Let's get right to it. So as with some of the other lectures, we're going to try to do the building blocks before we get to the actual thing. And the first building block here is the idea of a sequence or a time series. So you might just have a bunch of numbers, 0.2, 0.3, etc., but these numbers are actually in a certain order. They're not just a collection of numbers. And we call that a sequence. And so we talked about sequences a little bit before, but if I have these numbers, I could make a plot. And if those were just 5 random numbers, it wouldn't make sense to plot them in order, but this is actually a sequence. For example, day 1, day 2, day 3, day 4, day 5. And so in the lecture video on convolutions, which you hopefully watched, we had a bunch of these sequences, and then we applied 1D convolutions to them to sort of transform the sequences. So here's where it gets a bit different. We need to talk about 1D signals. So I'll use signals and sequences kind of interchangeably. We need to talk about these 1D signals with multiple features. So for example, let's say the sequence is over time. We're measuring something in Vancouver. So the previous thing could have been the temperature in Vancouver, but now we have the temperature, the wind speed, and the rainfall. So every day we measure those 3 things. Then we can make a table out of this. So on day 1, temperature was 20, wind speed was 0, rainfall was 0. On day 2, we had 3 more measurements. On day 3, we had 3 more measurements. And so this is a sequence, but instead of just being a sequence of numbers, it's a sequence of feature vectors, essentially. And so we could put these in a NumPy array. And when you look at this NumPy array, it has the same data as the table up there. There's really 2 ways you could think about it. You could think about it as 3 sequences, the temperature sequence, the rainfall sequence, and the wind sequence that are kind of separate from each other. Or you could think of it as a sequence with 3 features. On day 1, we had these 3 measurements. On day 2, we had these 3 measurements. And that is how I want you to think about it for today. So this type of thing, or if I scroll up, this type of thing is going to be our training example, which is very different from what we're used to. The whole last year until now, the training example, the feature vector was always just a vector. It was a one-dimensional entity. It was a row of our X matrix. Now, our input is a 2-dimensional entity. It is a time series of features, and we may have a label associated with that if we're doing classification, or a target if we're doing regression. But the input is this 2-dimensional entity, not just a column, not just a row, a one-dimensional vector of features. And now, if we want to store our entire training data set, before we had X, it was a matrix. Remember, the rows were the training examples, the columns were the features. Now our thing storing all of our X is actually a 3-dimensional array, because each entity is this 2-dimensional thing. It's a time series with multiple features, but we also have the number of training examples. So if we stored the whole thing, it would be number of training examples by the length of the time series by the number of features. Any questions or comments about that? As you'll see, pretty much the whole lecture today, it's all about the shape of the data. That is 90% of what we're going to be talking about. So the first shape we're dealing with here is that X is now what I'm calling n by t by d, where it used to just be n by d. OK. So now we get into 1D convnet. So convolutional neural networks, also known as convnets. There are various flavors of them, 1D, 2D, 3D, et cetera. We're going to start with the simpler case, 1D. And so in Keras, we have what you had before was a dense layer. Now we have a conv 1D layer. And what it does is it transforms an example, roughly speaking, from some sequence length with D0 features to that sequence length with D1 features. And it does that doing a bunch of convolutions. But keep in mind, our dense layer before took us from, say, 100 numbers to 10 numbers, or 5 numbers to 2 numbers, or whatever. We still have that happening here. If we had rain, wind, and temperature, that was 3 features. Our layer is going to transform us to some other number of features. But there's this extra dimension that's just tagging along, which is the length of the time series. And we'll see that a lot more in a minute. And as I said, there's going to be a bunch of convolutions when we do that transformation. And the filters for those convolutions, those are going to be the parameters we're learning. So before we called them weights, now we're calling them filters. But all those numbers inside the filters, so in the video, there was like an averaging convolution and all those kinds of things. So it was convolution with some filter. We're going to be learning those filters with convolutional neural networks. OK, let's look at some code. So this is Keras code, but now we have a conv1d layer instead of a dense layer. And I want to just read what all of these numbers are. So let's say we're starting with just a one feature thing. So temperature in Vancouver, day 1, day 2, day 3, day 4. That's this input shape over here. It says that capital T is 100, so we're measuring over 100 days, just one feature. So say temperature over 100 days. And the output number of features is 5. And so we're going from one feature to 5 features. And this kernel size is the size of the filter. So you've seen that in the video as well. You could have a little filter, you could have a big filter. But we're going to be getting these 5 features by doing convolutions with, in this case, just 3 numbers in them. And we're going to be learning those numbers. So you can already see how many little parameters there are to keep track of. This is a very detail-oriented exercise. But even in this one layer, we have the original number of features, which we had before. We had the new number of features, which we had before. But we have 2 new players compared to our dense neural networks. We have this kernel size and the length of the time series. So I can call model.summary, and it tells me that the output shape is 100 by 5, which kind of makes sense, because we started with, say, 100 days in one feature, and I just said we were going from one feature to 5 features. So now coming out of that layer is 5 features, or you could think of it as a time series with 5 features. So let me show you a picture. We can come back to these weights in a second, but I want to show you the picture. So here's perhaps my original time series with 100 points in it. I just made it up. It's not important what the values are. But what we're going to do to get from our 1 feature to our 5 features is we're going to have 5 different filters, and we're going to convolve this input signal with those 5 different filters. And what we're going to get is something like this. So the black is just reproduced. That's the original one. But remember, convolution is some operation that we do to a signal, and we get out a new signal. So how did I get these 5 curves? Well, I just have random filters right now. I didn't train the neural network. So I just took that original black curve, and I convolved it with 5 random filters. And each of those filters happened to be length 3 because that was a hyperparameter of the model. Questions? Yes, Anas.
Shouldn't the range grow because you convolved?
Right. So there's some issues about the boundaries, the range growing or shrinking. What I've done in the code is I've set this padding same for the entire lecture, just so we don't have to worry about that. That makes it extra confusing. And then there's an optional section in this notebook you can read that goes into the details of that. Sam.
Where does the randomness come from? I don't see that. How you get the 5 different.
This is random just because I haven't trained the neural network, so it just initializes with random weights. In this case, random filters, just like a regular neural network. So there's no meaning to these things. I'm just trying to show you the data type that's coming out of the layer. So the data type coming in was that black line, a sequence with 1 feature, and the data type coming out was this thing of size 100 by 5, which we can think of as these 5 time series, or alternatively, this 1 time series with 5 features. Yes, Rock.
So is the kernel size the number of weights in the convolution
filter?
Yes, the kernel size is the size of the filter. So I have the original signal. It has length 100. I'm convolving it with a little filter of length 3. So each of those filters has 3 numbers, which is a perfect segue into what I wanted to do next, which is this part I skipped where we actually look at the weights. So what is the shape of the weights? It's 3 by 1 by 5. How does that make sense? Well, we have 5 different filters. That's how we got those 5 different curves. So we started with 1 curve. We ended with 5 curves. We had 5 different filters, and each one was of length 3. So I can look at the weights, and here they are. The first curve on that plot was convolving the original signal with this filter of 3 numbers. The second curve on the plot was convolving that original filter with these 3 numbers. Yes, Aman.
What biases come into play in the picture?
Yeah, so I'll get to that in a second. Yeah. Yes, Reiko.
These 3 numbers were the ones that were sliding along.
Yes.
Yeah.
These 3 numbers are the ones that were sliding along. So I took the first 3, I was sliding them along. That gave me that first output curve. I took the next 3, those were sliding along, gave me the second output curve. That's why I got 5 output curves, because I have 5 filters here. And these filters are going to be learned when I call fit based on some loss function that we'll get to later. Other questions? Okay, we're going to be doing a bunch of these. So, yeah, this is not so important. What's important is that when I call predict, and I look at the shape coming out of predict, we should be able to interpret this now. The shape coming out of predict is we have just a single example. That's the one. We have 100 days. That hasn't changed. But now we have 5 features instead of just the 1 feature. The original feature was maybe temperature. These 5 features we don't really have interpretations for. Just like when we talked about neural networks last week, we had 100 hidden units. We didn't really have interpretations for what those features meant in the intermediate representation. It's the same thing here. We just have 5 whatever features that the neural network is deciding to learn. Okay, so let's do another example. That's going to be that exact same, but I have this 2 here. Input shape is 100 by 2. Everything else is the same. So now my input was actually, say, temperature and rainfall. It was 2 features for 100 days. And I still use filters of size 3. I still have 5 features coming out. And so now, my weights, now we see the shapes are starting to get messy. I already have a 3-dimensional array here. I have, in a regular neural network, if you just had 2 features going to 5 features, we would have a 2 by 5 matrix. That's what we were doing all last week. Now, we have that 2 by 5, but we also have this extra dimension of 3 because instead of each element in that 2 by 5 matrix, we actually have a filter of length 3. So we've replaced one of those weight elements with a filter, and let me show you this picture that I drew on my board and took a picture of. So we had these circle and arrow diagrams from last week. We have the circle and arrow diagrams now. I want to emphasize the very, very high degree of similarity between this and what we saw last week. The difference being that in each circle, last week we had a number, and now in each circle we have a sequence of 100 days. And before, each of these arrows represented a multiplication. We took the number in the circle, multiplied it by the weight, and then we were adding all those up to get to the output circle. That multiplication operation has been replaced by a convolution. So now, how do we get to this squiggle up here? Well, we take this input signal, convolve it with the filter, and we take this input signal and convolve it with that filter, and then we add them up. Just like last week, we're adding up all the things coming in from all the arrows. All that has been preserved. Questions about this picture? Yes, Gaurav.
So this will be 1 dimension only, like whatever we are inputting to the function, like ReLU or something. That will be.
I'll get to ReLUs in a second.
Just I want to ask, like, what will this output after filter? What will be the output? Will it be scalar or a vector?
It's this squiggle that I've drawn here, so it's still a sequence. We started with 2 squiggles, meaning 2 sequences, like rainfall and temperature. We've applied the layer, now we have 5 squiggles. So the shape of the 5 squiggles is 100 by 5. Our data shape was 100 by 2. We transformed it to 100 by 5. Just like in a regular neural network, transforming from 2 to 5, but now it's 100 by 2 to 100 by 5. And the question is, how many parameters do we have here? So in the fully connected case, you would have said, well, there's 2 here, 5 here. It's a 2 by 5 matrix. I have 10 weights. That's true. I still have 10 arrows here. But each arrow is a filter now that I'm learning instead of just a number. So how many parameters do I have here? 2 by 5 times 3. Because, and I tried to draw it here, each arrow has a little filter associated with it. And so when I'm counting the number of parameters, instead of the number of weights just being 2 times 5, the number of weights is 2 times 5 times 3, which is what I have here, 30. And then going back to your question about biases, same as before. Each circle gets a bias. So I have some bias, and I'm just adding it to my squiggle here. And so the total number of parameters here is 35. If you can look at a convolutional neural network and figure out how many parameters it has, that's the way to know you really understand what's going on. And if I just scroll up here for a minute, you can see there really are 35 parameters. So questions about this picture? Yes?
So
For Khan.
each of these circles, like say in each of these 5 circles, so you have 100 by 2, like say each circle has both the features or just...
No, so each circle just has a sequence of length 100. These 2 circles together at the input are the 100 by 2.
Yeah. So how about at the output?
At the output, I have 100 by 5. I have 5 sequences of length 100.
Okay. So this is somehow, like say, transforming the data.
It is transforming the data, which is exactly what neural networks did last week, regular fully connected neural networks, as we call them. It's transforming the shape of the data, which we've already seen happen, except instead of going from 2 features to 5 features, we're going from 100 by 2 to 100 by 5.
So exactly in this sense, we don't know, like say, what these features are.
We don't have an interpretation for these 5 features coming out. Correct. Yes, Derek.
These sequences that you put in, so we're using the example of time, in your video you talked about space. Are there any other kind of sequences that get played with?
Sure. So Derek's question was, here we're talking about time. I talked about space. Sure. I mean, you can have 1D spatial data, 2D spatial data, 3D spatial data. You can have video, which is like space, and time. You can have all kinds of different things.
So is it generally just sequences in space and time? Like
It doesn't even just have to be space and time. The whole point here is that our training data has some sort of structure to it. It's not just a million columns in our pandas data frame where you could reorder them and it wouldn't matter, but there's kind of a shape or a structure to the data. Kenneth.
There are 2 arrows pointing to the first node on
2 arrows pointing to this.
Does that mean that the weights of each filter is half?
Well, it means they're being added together, which was exactly what was happening before. So before, if we had 2 arrows, what was happening here? We were taking this number, multiplying it by this weight, this number, multiplying it by this weight, and we're adding them together, because that's what matrix multiplication does, right? It's a dot product between the vector of the 2 weights and the vector of the numbers. It's the same thing here. They're getting added together. Rock.
Why do we want to add, like, for instance, the rainfall and the temperature together?
Why do we want to add the rainfall and the temperature together? Well, that's actually what we were doing before. I mean, if you just used a regular neural network, you didn't have time, you just had rainfall, temperature, and 50 other features. That's what we were doing last week. You were just taking all those things, multiplying them by weight. It's like, why do you add things together in linear regression? Because it's the same intuition. You take the features, you multiply them by coefficients, and you add them together. That's exactly what's happening here, except with neural networks, we're going to have a bunch of layers of that and those nonlinearities, but it's the same idea. Okay, so this is really the fundamental picture that kind of defines everything we're doing today. Yes, Victor.
So the filter will be the same for each of the lines?
No, each arrow has its own filter. So just like here in a regular neural network, each arrow has its own weight that's being learned. Here, each arrow has its own filter, and that's why the total number of parameters here is 2 times 5 times 3. So in other words, we have 10 arrows. Each arrow has 3 separate numbers, so we have 30 numbers in total that we're learning. Okay, some key points here. We probably talked about most of these. Yeah, basically what I want to say, summarizing all this text, is that our weights are now stored in a 3D array, like 2 by 5 by 3, whereas before our weights were stored in a 2D matrix. Okay, so I can make a training example here of size 100 by 2. I can call predict, and I can see the shape is 100 by 5. That's what we expected. And I can do the same thing with 1,000 training examples. 1,000 by 100 by 2, call predict. We get 1,000 by 100 by 5, and that's the same Keras model, right? This Keras model is going to work regardless of how many training examples I put in. That's not part of the architecture. The architecture is about the number of features, and you can pass in however many examples you want. That's all the same as things you've seen before. Okay, so I'm going to go to 2 layers now. I have this layer that we just talked about, and I have another layer after it, and just to spice things up, I changed the kernel size to 7, and I changed the number of features to 4. So now we're going from 2 features to 5 features to 4 features, which we happily did last week in our non-convolutional world. We're just doing the same thing here. I can see the summary. I'm going from 100 by 2 to 100 by 5 to 100 by 4. I've applied a ReLU at every layer, which just gets applied to every number in the output squiggles. And, well, let me show you the picture, and then we'll look at the weights. So here's the picture. I've explicitly drawn the ReLU here just to say it's transforming the output squiggle into another output squiggle. So the ReLU is not changing the shape of anything. So here's our first layer. Those are those parameters. And here's our second layer. We're going from 5 features to 4 features. It's all exact same as last week, except we have an extra dimension everywhere. How many weights are there in this mess of red arrows? Well, last time we would have said 5 times 4 is 20. Now I'm saying 5 times 4 times 7, because I picked my filter size of 7. So each arrow has a 7-length filter hanging on there. And so the number of parameters here is 5 times 4 times 7. And again, I have 1 bias for each circle on the output, so plus 4. Now I get this 179 total parameters. Questions about this? Yes, Derek.
So just you've got biases kind of hidden on a separate kind of level almost.
Yes, I'm just not drawing the biases.
Yeah, okay.
But you have one for each circle at the end of a layer.
But the point I'm trying to get at is they're kind of separate from these convolutions. Because before we grouped them all, we had the weight, the slopes, and the intercepts all together in one matrix, but now we kind of split them.
Yeah, the biases you can think of as separate. Yes, sure.
It will also be 100 dimensional, right?
No. No, you do not have a separate bias for each day. You just have one bias, and it's added to every element in that squiggle. So that's why I'm just counting here 5 biases here and 4 biases here, not 500 and 400. And notice, by the way, critically, maybe one of the most important points of today, the number 100 is not appearing in my calculation. That is the entire power of this approach, is that if we had 100 days or 1,000 days or 1,000,000 days, the number of parameters in our convolutional layer, that doesn't enter into it. And so that allows us to have not a ridiculous number of parameters in our model. Tom?
what shape is the bias? Does it match the ones that we're putting in, or is it just like a single number? Like
It's just a single number per circle. So for this first layer, it'd be 5 by 1, and the second layer would be 4 by 1.
Thank you.
For kind.
So in this example, you have the convolutions as a vector, right? Not as a matrix, because the features is a matrix, right? Of 100 by 2 initially, and then you multiply it by the convolution of one vector, right?
Well, think of, okay, I know, yeah, so think of this as temperature and rainfall, and then temperature gets convolved with 5 different filters, and rainfall gets convolved with 5 different filters. So you just think of those as being separate for the purpose of applying the 1D convolutions.
Because I'm kind of thinking through the video that you have from, say, from that lecture, because you were actually doing the matrix multiplication with the features.
Yeah, okay, don't worry about the matrix multiplication. In the video, I talked about how this is equivalent to matrix multiplication. Let's just ignore that for now, because it's going to cause more confusion than it's going to help. Okay, so let me look at the weights here. So 3 by 2 by 5. That's what we just talked about in the picture. And the biases are just a 1D array of 5 biases. Second layer, 7 by 5 by 4, and we have 4 biases. So again, how do we read this? We have 2 features, 5 features, so 10 arrows, and each arrow has 3 numbers. Then we have 5 features going to 4 features, so that's 20 arrows, and each arrow has 7 numbers. So again, we need 3-dimensional arrays to store all those parameters. And this 5 and this 5 have to be the same, just like in regular neural networks where you have a 2 by 5 matrix and then a 5 by 4 matrix. Those have to match because they're sharing that dimension. Okay, this is some optional stuff where I've implemented fully connected neural networks and convolutional neural networks just a minute, and it's kind of from scratch. If you want to get more into this, I definitely recommend going through this, but it will probably take you a while. So I'm not going to do it in lecture, but it's useful if you're interested in more of the details. Okay, Anas, where did you go? Yes.
So I just want to understand if it's like possible. Could you have like convolution layers and then like normal layers?
We will have that later today, yes. You can have convolutional layers and then normal layers, dense layers. We will do that. Okay, next thing we need to talk about is something called pooling. So here we have our first layer from before that goes from 2 features to 5 features, sequence length 100. And we had this before. I can make a training example with some random data of 100 by 2. I can call predict. It's 100 by 5. That's the same as before. But now I'm going to add this new thing called the max pooling layer with pool size of 2. And this is the first time we're going to mess with that number 100. What pooling is going to do is it's going to change that 100 into a 50. In this case, it's max pooling. So it's going to take every pair of days, day 1 and day 2. It's just going to take the max of those, the larger. Day 3 and day 4, it's going to take the larger of those and only keep that. Day 5 and day 6, it'll take the larger of those and only keep that. And so if I call model.summary, you can see the shape after the pooling has, instead of having 100 days, I just have 50 time steps now. And this is a popular thing people do in convolutional neural networks. And now you can see that I've reduced the shape. So why do people do this? It's going to help reduce the number of parameters, as you'll see in a minute. It also is supposed to help with invariance, but let's leave that for a minute. I just want to show you the picture first. So here's a picture of max pooling. It isn't a layer in the regular sense, but it does change the shape of our data. And all it does is for each circle here, it just says I'm going to throw away half of my time points. I'm going to replace each pair of time points with the bigger of the 2. Or if I did pooling size equals 4, it would replace each 4 time points with the biggest of the 4. And so I'm actually reducing the length of the sequence here. Anas?
What's the intuition behind like max pooling? Why aren't we using like average pooling or something like that?
Yeah, so there's some like kind of neuroscience history of this, that if you're trying to identify an object in an image, like maybe the object's over here and maybe the object's over here, but I just want to know if it's there, so I'll just check if it's here and check if it's there and kind of take the bigger response of those two. I think by now, like, we are departed very far from the sort of history of neural networks, and if people are still using something, it's just because it works. That's my take on it. But also, as we'll see in a minute, we'll see why it reduces the number of parameters and why that's a good thing. So just hold on for that. Okay, break time. Let's resume at 11:06. Okay, we need to resume. So there was a bunch of questions during the break about this issue that in the video, in the video I emphasized that convolution can be thought of as matrix multiplication. I really don't want you to be thinking about that today because that's just going to mess up our understanding. It is a fact worth knowing that a convolutional neural network is just a special case of a regular neural network. If you think about representing convolution as matrix multiplication and you saw that matrix with a bunch of zeros, blah, 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 you should know that. But we are not really thinking about it that way or implementing it that way. It's just, it's important to know. But, so for example, someone asked me, why do we have all 10 arrows here in this picture? I thought the whole point of convolutional neural networks is that you don't have all the arrows. So the problem is that the picture I'm drawing here is a specific kind of picture where the arrows represent convolutions. If you go back to the original kind of picture you draw, where you flattened out all the inputs, so 2 by 100 became 200 things, and you just flattened everything out and pretended it was a regular neural network like last week, then you wouldn't draw all the arrows because it's this special matrix with a bunch of zeros in it, and a zero in the matrix is the same as not having an arrow, etc., etc. But yeah, I just want to put all of that aside for today and think about this type of picture. And in this type of picture, everything is connected in that there is a convolution from every feature to every feature. Questions about that? I should just cut that out of the pre-class watching, I think. And maybe it could be post-class watching. But yeah, we don't want to be thinking about that today. Okay, flattening. So let's say we want to do classification on the MNIST digits like we were doing in lab. So that's fine. But here's the problem. Remember from last week, our output of our neural network was the 10 probabilities of the different digits, 0 through 9. So I want the output to be 10 numbers, just like it was last week. I want those 10 probabilities coming out. But the shape of everything today has been two-dimensional, 100 by 2, 100 by 5, 50 by 2, whatever by whatever. Things coming out of my convolutional layers keep being two-dimensional, number of time steps by number of features. But the thing I want out is one-dimensional, just 10 numbers. So that's why we need to talk about this flattening step. So first of all, you've probably seen flattening before, just in the sense of numpy dot flatten, where I have a two-dimensional numpy array I can call flatten, and then I just stick it all into a one-dimensional array. That is the spirit of what we're about to talk about. And here it is. It is literally a Keras layer called flatten. And what it does, it doesn't change anything. It just changes the way you think about. It doesn't change the numbers. It only changes the shape that the numbers are organized in, just like this. This does not change the numbers. Look, you still have 0.6718, whatever. Those numbers are not being changed. Only their shape is being changed. That is analogously true with this flattened layer. So look at model.summary. Our shape was 100 by 5. Well, our input shape was 100 by 2. Then we did a convolutional layer, went to 100 by 5. Then we did a max pooling layer, went to 50 by 5. Now we call flatten. That just takes that 50 by 5, so 50 time steps, 5 features, and just flattens it into 250 numbers. They're all, again, these are hidden activations now. These are these intermediate features that the neural network is making. They don't necessarily have meaning to us. But we can just flatten them. And now we're like in the domain of regular neural networks again from last week, where our intermediate representation is just a 1D array. And hey, we had 10 different classes, and this is 250, and that's not the right number, but that's fine, because now we can just stick a regular dense layer on the end of this thing, going back to your question. And that regular dense layer can change the shape from 250 to 10 by having a 250 by 10 matrix in there a la last week. Nothing convolutional about it. Okay. Questions about that? Kansha?
The extra dimension in the earlier one, we got it because we had 100 days data for temperature or some other variable.
Yes.
Where is it coming in the digits data?
Sorry. Good point. Okay. The digits data set, the inputs are actually 2D sequences, and we're going to talk about that in about 10, 20 minutes. Right now, we're just talking about, so it wasn't, let's say you have, I don't know, some city of Vancouver measurements, and you're trying to classify it into 10 classes, and then you want those 10 probabilities. But yes, we don't really want to go there yet. You're right. There was another question, maybe? Okay, so here comes a major confusion warning. We have two types of flattening, or 2.5 maybe types of flattening. This gets people all the time. So the first type of flattening we have is parameter flattening for optimization software, which has nothing to do with what I just said. Last lab, you were implementing your neural networks, and you had that combined params thing that said you have a bunch of weights and biases, and you just need to stick them all into a giant vector so you can pass that into an optimization software that expects a giant vector. That's I'm calling parameter flattening. So you have a bunch of parameters all over the place. Doesn't have to do with convolutional neural networks at all even, just regular neural networks. Gather all the parameters, stick them in a giant vector. Also called flattening often, nothing to do with what I was just talking about. Then there's data flattening, which is related to what I was just talking about, but there's just two types of that, two subtypes of that as well. Type 1 is the visible data flattening, which you did last week on your lab with your MNIST digits. They were, whatever they were, 64 by 64 images. And because we hadn't learned about convolutional neural networks yet, the best we could do last week was flatten that image into a 64, or maybe we're using the 28 by 28 ones. Anyways, we're flattening them into a vector of length 28 squared because we need each training example to be one-dimensional as it's been for the last 6 months. That was flattening the input data. We were flattening the images. Here we're doing a similar type of data flattening, what I just talked about, but it is a hidden data flattening. We're not actually flattening the raw images, but we're flattening this intermediate representation, which we don't really have a great interpretation for, of size 50 by 5, those 5 made-up features that the neural network made up, 50 time steps. We're flattening that into one giant thing of length 250. So be careful that you know what type of flattening you're talking about, because people can get tripped up by this a lot. Any questions? Yes, Shivam.
Yeah. Before, your weights were not changing with respect to, let's say, time, 100 data points. But by flattening it, will they change by, let's say, 50? Like, will 250 data points will have different weights?
I wouldn't say 250 data points. So this 250, by the way, this none dimension here is for the number of training examples. So we could just have one training example or 100 or a million. Doesn't matter. As I was saying before, that has nothing to do with the architecture of the neural network. But this 250 has nothing to do with the number of examples. It's 250 of these kind of made up features.
But they will have their own weights. Earlier you were saying that 50...
Yeah. Okay. So yes. When I add a dense layer after this, then for the first time ever, the number of parameters is going to depend on that original number 100. Yes, Gaurav.
Ordering of these 250 weights matter because like,
No, the ordering of these 250 weights don't matter, and we talked about that last week. So if with your regular neural networks from last week, you went from 100 features to 50 features, the order of those 50 features made no difference. So however they decide to flatten it, as long as that's kept consistent between training and testing, it doesn't matter. Okay, so be careful with this terminology. Right, and this is the point we just talked about with Shivam, which is, well, we'll get to that in a second. Okay, so here's my first end-to-end example where it's actually going to do something. I'm going to do 10-class classification where my inputs are 100 by 2, so say 100 days, 2 measurements. I'm going to get out these 10 probabilities. Here I have a convolutional layer, a pooling, another convolutional layer, a pooling. You can't have a dense layer until you have a flattening. I flatten it. My shape of my intermediate data is no longer two-dimensional. It's no longer time by features. It's just a bunch of features. And then I can apply a dense layer. And I could apply as many more dense layers. After flatten, I've kind of transitioned into last week territory, where I'm just at one-dimensional data. I can have as many dense layers as I want, do all the things we did last week. But we don't want to do that from the beginning. These convolutional layers at the beginning are very important. They have a lot of benefits. So we don't just throw away the structure of the original data and flatten it all into some giant vector. We don't have nearly as many parameters as we're going to see in a second. So let's look at the parameters. So that first convolutional layer has 35 parameters. We saw that before. That second convolutional layer has 112 parameters. We saw that before. Now maybe it would be less confusing to get rid of these. Okay, so now we have that 250 that we had just a minute ago. And now I'm going from 250 to 10. So now this 2510 is last week's stuff. 250 to 10, we have a 250 by 10 matrix plus 10 biases. That's 2510. So what I want to point out to you here is look how many more parameters we're getting from the dense layer than we got from the convolutional layers. That is not unusual. And it's, again, because of what we just talked about, that 100 days has only finally kicked in. Before, the fact that we started with 100 days was being carried down in terms of the shape of the data, 100 time points, 50 time points, maybe we did more pooling, 25 time points. But the number of parameters in those convolutional layers did not care about that 100. They only cared about how many arrows we had, which was 2 features, 5 features, and they only cared about the filter size. And so that's kind of the beauty of convolutional neural networks, is not ending up with a ridiculous number of parameters. You're not taking a 1,000 by 1,000 image, flattening it into 1,000,000 pixels, and then having a 1,000,000 by another 1,000,000 matrix with a, whatever that is, trillion parameters or something totally insane. You're kind of making the data shape smaller and smaller before you face reality of having the number of parameters actually depend on the number of time steps. So in other words, if I change this 100 to 200, watch this number 35 and watch this number 2510. The 35 stayed the same. The convolutional layer did not care that I added more days. But the dense layer cared because this 250 turned into 500. And so that moment of reckoning came after the flattening, where suddenly the number of parameters did depend on the number of days. Questions or comments? Ithar?
When it's specified what those filters are doing, like averaging, like integration.
Yeah, what are those filters doing, averaging, etc. That is what you're learning when you call .fit and run stochastic gradient or whatever. It is optimizing those filters themselves to do whatever the heck needs to be done to minimize the loss function. So if you're doing, so that's, it's learning those filters automatically. Should I do averaging? Should I do this? Should I do that? You're doing like your gradient descent with respect to those parameters of the filters. You're wandering around in filter space trying to minimize the loss. So all that is getting chosen only based on the data and the loss. Tom?
Is this the reason why we do the connet is essentially to like save space and computing space first, and then, or does it actually not save it?
It's not just about saving space. So the question is, why are we doing this just to save space? Yes, you're right, having 1 trillion parameters would be computationally intractable, but it would also be an insanely complex model that is complex in ways that are not useful, because the kind of intuition for convnets is, well, people usually talk about images, so I could talk about images, like you're looking for certain things in an image, like edges or circles or whatever, and you can look for circles over here in the image, and over here, and over here, and over here, and you just need to learn those filters that says look for a circle, and then it's going to kind of slide through the signal and look for it everywhere, as opposed to saying things that are useful for me to extract from this part of the image are completely, I'm going to learn that completely separately from what's useful. Or for the Vancouver thing, like maybe you're looking for fluctuations in temperatures. That's going to help you predict your bridge falling down, say. And so you just want to know, it was a really hot one day and really cold the next day. And then you learn that's useful to look for, and you look for that in January, and you look for that in February, and you look for that in March, as opposed to relearning that lesson over and over again. So it would just be massive over-complexity. You would have massive overfitting problems, because you want to kind of translate your knowledge of what you should be extracting across that time window or across that image. Jarvis.
How do the filters get different? If it's just trying to minimize, would the filters become similar to each other?
Well, you initialize randomly, and then it kind of works from there. It's just like, how did the weights become different in a regular neural network? You initialize randomly, and then they do their thing. And if you initialize differently, you would get different results. Furkan.
It is like, say, the main advantage of this convolution neural network over the regular one is that you have less parameters and they are less, like, so your model is less prone to over.
Yes, the main advantage is that you have fewer parameters, but you didn't just throw away parameters randomly in a silly way, but you actually took advantage of a pattern that, hey, things that are useful in this part of my signal may be useful in this other part of my signal, so let me not relearn that separately. So you throw away tons and tons of parameters, but in a sensible way, and then you get very effective models that are not kind of relearning the same lessons for every part of your image. But yes, at the end of the day, it comes down to complexity and the number of parameters. Okay. Yes, we talked about that. So for regression, it's all the same thing, except I would just have a dense of 1 at the end, which you've seen last week. So with regression, I just want one number. Everything else is the same. Here I have 251 parameters, my 250 plus my bias. Okay. Right, so I can just call predict and show you that you just get out a number, but that shouldn't surprise you because you had a dense of 1 at the very end. So then you just stick on your loss function, all the same as last week. Doing regression, you can use squared error or anything else that you feel like using for classification. You can use softmax or everything else that you feel like using. That's all the same, and then you just optimize the heck out of it and learn, instead of learning those weight matrices now and biases, now we're learning those filters and biases. And so there are now those 3-dimensional tensors of parameters, number of features in by number of features out by filter size. Okay, this I'm skipping as well. I marked it as optional. There's something called strided convolutions that when you're sliding the window around, you don't put it at every single spot, but you kind of jump. I put it here, put it here, put it here, put it here. So that's a pretty popular thing, and you can read over this later if you're interested. But for now, I'm just going to skip it. There was also this, I forget who asked it, someone asked it earlier, shouldn't the 100 change a little bit? You convolve a 100 thing with the filter of size 5, shouldn't the output length change slightly? So here's another optional section that you can read through about that, which I'm doing with the padding argument. Skip that as well, but what I want to get to now is two-dimensional convnets, which are actually the ones you're going to use in your lab this week because we're going to be operating on images. So all that was one-dimensional convnets. When do you use one-dimensional convnets? When your inputs are time series or whatever sequence. So your inputs are two-dimensional, number of steps by number of features. Your giant X thing is three-dimensional, number of training examples by number of time steps by number of features. Now we're just going to take everything we just said and add one dimension to it. And so it's going to get messy. Here we go. A two-dimensional signal is typically, oh, Anas.
Sorry, so it's two-dimensional convolution because it's a grayscale image because we removed the other two channels, or?
That is not true, and I will get to it in a second. Yes, but it's a very important point. Okay, so now that we're going to deal with two-dimensional signals called images. And so basically we have structure in 2 dimensions now. So I'm going to use h and w to denote the height and width instead of t, which was my number of days from before. So this is height 50, width 100. And so I was plotting those squigglies before, and now we have an image instead. Okay, so actually to get straight to your question, Anna. So before we were talking about 1D convolutional layers when our data was 2D. It was number of days by number of features. That's what we saw at the very beginning an hour ago. Rain, wind, whatever, day 1, day 2, whatever. Now, we've upped everything by 1 dimension, so it's going to be 2D convolutions, which means our data is going to be 3D. Our data is going to be our first spatial dimension by our second spatial dimension by the number of features. We still carry that over from before. So the kind of structured part of it where the order matters, there's now 2 dimensions of that where the order matters. Think before about the rain-wind thing from the beginning of the lecture. The day dimension, the order mattered. You can't just swap day 7 with day 22 because they go in order. But the order of rain, wind, whatever, you could reshuffle them. That's how you differentiate in your mind, is this a structured dimension or a regular dimension like we're used to? Now we have 2 structured dimensions where the order matters. I can't just mess with my image and change the rows and columns. But I have this other dimension, which is the number of features, which we're actually now going to rename the number of channels, just by convention. Number of features, number of channels, same thing, just the terminology. And when have we seen before this idea of an image with multiple features or channels? Actually, we saw it in the seam carving lab when we had RGB images. So we had the red channel, the green channel, and the blue channel. That is an example of an image with 3 features or channels. It is not the only possible situation where you would have an image with multiple features or channels. It's just a very common scenario of where you have an image with multiple features or channels. So now our data is 3-dimensional, height by width by number of channels, where before our data was 2-dimensional, number of days by number of features. Right?
The grayscale image, how many channels?
1. The grayscale image had just 1 channel. It was just like temperature in Vancouver only had 1 feature, which is allowed. The grayscale image is the same thing. It just had 1 channel, the intensity of the pixel. But in general, we need to allow for multiple, and then the 1 channel is just a special case. Rock.
Yeah, so is it right to say that the number of the dimension is actually named by the number of dimension of the convolutional filter?
Yes, but if it's conv and 2D, your data is going to be 3-dimensional. If it's conv 3D, your data is going to be 4-dimensional. The conv 2D means you have 2 dimensions of structure in it, and then you always have that 1 extra dimension for number of features. But yes, our filters are about to be 2D, as you'll see. Okay, so here's a picture of Milad that I loaded up. And you can see the size of it, 756 rows, 506 columns, and 3 channels. So again, just reiterating that our data is now 3D, and reiterating that it is often 3 channels because of color images, but could be any number of channels. Please don't think it's just 3, Tom.
Have to be a JPEG or?
No. The JPEG is, as soon as we load it, it's just a 3-dimensional NumPy array, and we don't think about it any further. And this could work for any 3-dimensional NumPy array.
So like the compression of like JPEG doesn't like affect how it comes in?
Well, imread like decompresses it, so that's not relevant, yeah.
Thank you.
Okay, so here's the conv2D layer that you've been waiting for. Here's the syntax. Kernel size is now a tuple because our filters are 2D. So it's 11 by 11 filter, a little square filter. This is the same. This 5, exactly the same. Number of features. We're just renaming it number of channels, but we have 5 channels now, exactly the same as the 1D case. And the input shape, I have to give, well, the height, the width, and the 3. Okay, so I went from 756 by 506 by 3 to 756 by 506 by 5, because I went from 3 channels to 5 channels. Exact same as before we were talking about with 1D. That structured dimensions just comes along for the ride. We had 100 days before, we have 100 days after. We have height and width, now we have height and width after. Reiko.
Does your filter have to be a square?
No, your filter doesn't have to be a square. Okay, so here's the picture. It's the exact same picture, except the squigglies, which were 1-dimensional sequences, are replaced by rectangles, which are trying to show images. And each arrow has, hanging off of it, a 2-dimensional filter instead of a 1-dimensional filter, because everything is 2D now. So for example, 3 by 3. And everything else is the same. So if you want to count the number of parameters now, well, you went from 3 channels to 5 channels. That's 15 arrows. Each of the 15 arrows has a 3 by 3 filter on it. So that's 15 times 3 times 3 gives you whatever that is, 135 filter numbers plus 5 biases is 140 parameters, which is, this is different kernel size. Anyways, which is the number of parameters here. Questions about this picture? Any?
Should we ignore the whole how to do the matrix multiplication for this as well when we're trying to understand it?
Yes. I still don't want to think about the convolution as equivalent to matrix multiplication thing. Again, each of these arrows is a convolution, and now a 2D convolution between this image in the circle and the filter for that arrow. And then again, you just add up all the incoming signals to get the output circle. Okay, so again, number of parameters does not depend on the input image size. However big picture of Milad was, same as before, that is not coming into this, and again, will not come into play until after flattening. So now we could take big images and not have crazy number of parameters. Because the number of parameters only depended on number of channels in, number of channels out, and filter size did not depend on the input image size. Derek.
Just taking this one step further, what's the difference between doing a 2D image like that with 3 channels versus one 3D?
I love that question. I was waiting for it. Okay, the question is, what is the difference between doing a 2D image with 3 channels and a 3D image? So for example, you might have like a volume image. Those are very different because built into this convolutional neural network is some assumptions about the structured dimensions. It's that you're sliding things along those structured dimensions. And then the feature dimensions are considered to be unordered. So you would not want to use a 2D convolutional neural network on 3D images. You would want to use a 3D convolutional neural network with 1 channel, if it was truly a volume. And likewise, for the Vancouver rain, whatever, you wouldn't want to use 2D convolutions with 1 channel. You want to match the dimension of the convolution to the number of structured dimensions, or ordered dimensions. Any?
So just to clarify, then if it was 3D, each square in the node is actually like a cube.
Yes, if it was
kernel instead of the matrix is also cube.
Correct.
Cubes. Okay.
Yeah, so for example, video is 3D. You have 2 spatial dimensions and a temporal dimension, and you could use 3D convolutional neural networks where the input is actually a video. Or it could be really a 3-dimensional image like some reconstruction of something. I want to keep going, so I'm going to cut off the questions for a minute. Just so I don't run out of time. Ugh, did I not run the code above? Here we go. Let me run it again. Okay, so remember I showed you this earlier today? I showed you what is the output of that layer. Well, I had a 1 thing, and now I have 5 things. This is the analogous picture. These are the 5 channels coming out when I put the Milad image in. So these are just random filters. I haven't run optimization, just a random initialization. But this is the equivalent picture in 2D. I started with an image with 3 channels, and then I transformed it to an image with 5 channels. And if I wanted to look at that, I would have to put it like this. So this is the 2D analog of this picture from earlier. The output shape is 756 by 506 by 5. And that's just one training example. Okay, yeah, that's fine. So this is, yeah, we can skip that. Okay. Warning, another thing where people often get confused. Do not confuse the filters and the activations. What I just showed you, those 5 milads, that was the activations. That was the hidden representation with 5 made-up features where I passed in that input image into the network. And here's a plot of the weights. Okay, so how many weights are there? Well, we went from 3 to 5, so we had 15 arrows. Each arrow had an 11 by 11 filter on it. One of these things you're looking at is an 11 by 11 filter where the intensity is representing the number. So each of these grayscale looking things is the filter. It would be too messy if I actually drew all the numbers. And I've arranged them into a greater grid of 3 by 5. Because I have 3 channels here, 5 channels here, so I have 15 arrows. So I arranged it in 3 by 5, and each filter is an 11 by 11 filter. And now people really start to get confused here because this is actually a 4-dimensional array. So maybe this is the first time you've had a legitimate use for a 4-dimensional array. I don't know. But that's what we have. Because before, in 1-dimensional case, we just had number of channels in, number of channels out, and then our filter length. Now we have number of channels in, number of channels out, and our filters are already 2-dimensional. So the total number of numbers here, as we just said, is 3 times 5 times 11 times 11, and that's how you get that 4-dimensionalness. And just keep in mind that what I'm plotting here is the filter. So here I'm plotting the parameters, the things that are going to get learned when I call fit. Over here, I was plotting the hidden activations, the data that was flowing through. Don't confuse those. You can draw both of them as pictures, but one is the data and one is the parameters, and they're completely different. So this is the data flowing through. This is the parameters. And you can see it's 4-dimensional. It's 3 features to 5 features. And each one's 11 by 11. Yes, Anna.
You call it the weight tensor?
Uh-huh.
So, like, what's like a tensor?
By tensor, I just mean some higher dimensional array. Like, in this case, a 4-dimensional array. Mm-hmm. Just array. That's all I meant. Okay, so here I have another picture for you that's showing this 4-dimensionalness. So if something is a 4-dimensional array in Python, that means to index it, you need 4 indexes. If I want to grab a number out of that mess, I have to go W of 2, 4, 0, and 1. And what am I talking about with 2, 4, 0, and 1? Well, here's my row number 2, my column number 4, and in that little guy, row number 0 and column number 1. So it's saying so the first index is, I'm going to scroll up here. The first index is which of these am I referring to? Number 2, that's this one. The second index is which of these am I referring to? That's this one. Now I've picked this arrow when I've said 2, 4. And then inside of this arrow, I have an 11 by 11 thing or a 3 by 3 thing or whatever, and I can index into that filter, and that's how I end up with 4 indexes or a 4-dimensional array. So it's all just what we just did plus one more dimension, but nonetheless, once you start talking about 4 dimensions, it's a lot more confusing just because it's very hard for us to think about 4 dimensions. But just if you're lost, anchor yourself back to that 1D convolution. And then just everything's 1 dimension more. The data is 1 dimension more. The parameter array is 1 dimension more. The convolution is 1 dimension more. The filter is 1 dimension more. Bring yourself back to that, and then try to digest this. Shivam.
By using convolutions, the number of arrows have reduced, but the number of things that we are learning kind of has, because in this case, all the number of arrows times the values in those filters. We'll have to learn all those.
Yes.
So, like, is it really a reduced?
Yes, it is massively reduced. The question is it, hey, the question was, hey, that sounds like a lot. 3 times 5 times 11 times 11, that sounds like a lot. Is it really reduced? Think about how bad it would be if you took that original Milad image that was around 1,000 pixels by 1,000 pixels, flattened it into 1,000,000 features, and then tried to use even linear regression. Or logistic regression. You already have millions of parameters. Just not even using a neural network, not to mention lots and lots of layers. As soon as you flatten that Milad image into 1,000 numbers, you're going to have, into 1,000,000 numbers, you're going to have millions of parameters. Here, even though we have a big image with tons of pixels, we can get away with just 100 parameters. So it is massively reduced. And of course, the bigger the image, the more reduced it is, because this is depending on the image a lot less. Okay, any questions about this 4-dimensional beast? Okay. So max pooling works the same way. It's called max pooling 2D. We specify the size is 2 by 2, so this dimension and this dimension, shrink them both by 2, but everything's the same as before. So we did 2 by 2. We halved these numbers to these numbers. So that's all the same as before. And now I'll do the whole end-to-end 2D convnet for the MNIST case. So here's what I have. 2D convolutional layer. Input shape is 28 by 28. Now I'm going to, start with 1 channel because they're grayscale images. I'm going to 32 channels. Then I'm going to 50 channels. Then I'm flattening. And then I have 2 dense layers afterwards. I said I was not going to do this, but let me start by doing this nonetheless. And we can delete it if necessary. Okay, so here's the summary. We have 28 by 28 images. We started with 1 channel. Now we have 32 channels. Then we max pooling. So now we have 14 by 14 images with 32 channels. Then we do another convolution, going from 32 channels to 50 channels. Then we do another max pooling. Then we flatten. So when we flatten, we had 7 by 7 images with 50 channels in our intermediate representation. So the flattened size is 7 times 7 times 50, which is 2450. And then the next dense layer has 128 units. So this horrible looking number is 2450 times 128 plus 128 biases, just like last week. But look at how we have tons and tons of parameters there after flattening. And again, to reiterate, if I change the image size, this number would not change. This number would not change. Only after the flattening, those numbers of parameters are getting affected by the image size. If I take away the padding equals same, then everything's just slightly more confusing because when I started with 28 by 28 images, I get to 24 by 24 images just because of the boundary conditions of the convolutions, which I don't really want to talk about right now, but which you're going to see when you do this in your lab.
I have a little disagreement here, actually. Like, I think after max pooling, your number of parameters will change depending on the image.
Well, we can try it. So here we go. So you're claiming this number is going to change?
Yeah. So, like, if you make it 24 by 24, if you change that, I think.
Change this?
Yeah.
It all goes back to this picture. All the parameters come from number of channels in, number of channels out, filter size. The pooling is not changing any of those. All those other dimensions, number of days or image height and width, those are coming along for the ride, as I'm saying. So max pooling can change these rectangles into smaller rectangles, but that's still not changing the number of parameters. Ryan?
When you flatten, doesn't that reintroduce all the complexity that you were kind of...
Yes. When I flatten, doesn't that reintroduce all the complexity that I was trying to avoid? Yes, but I have already made things so much smaller before I got there because of the pooling and because I can pick this 50 to be whatever I want. So I'm never in the domain of that original 700 something times 500 something. So yes, I get it back, but it's a pared down version of that original complexity before I dare use a dense layer. Okay. What's here? Pretty much the same thing. Oh, this is exactly what Anas was asking me. Change the input size. I had that in the notebook and see that the number of parameters are the same. So now, just in the last 3 minutes, I want to summarize the different types of networks. In fact, if you think about last week's dense or fully connected or whatever you want to call them networks, you could actually think of them as 0D convolutions. And then you have this table of all the shapes. So before, our data size was just number of features. That was like the 0D case, 0 structured dimensions. Then when we went to 1D, we had number of days by number of features. Then we went to 2D, we had height and width by number of features. You could go to 3D convolution. For example, video, again, has height, width, and number of time steps. Everything steps up. So that's the data shape. Then you have the parameter shape. In the original case, the fully connected convolutional network, the parameter shape was number of features in by number of features out. It was a matrix. Now we kick that up by 1 dimension every time, which is how we got to this 4-dimensional array for 2D convolutions. Because it's always number of features in by number of features out. But then we had these extra 2D from the filters. And so with 3D convolutions, you have a 5D array to store all the parameters. You have number of features in by number of features out by a 3D filter. And yes. And the kind of basic operation is just being changed from 1D convolution to 2D convolution to 3D convolution. You could kind of think about multiplication as 0D convolution. Multiplication is the operation we had last week because you're taking the weight thing on the arrow and you're multiplying it by the number. Then you're adding them all up. Now we're taking the filter, convolving it with the sequence, and adding them all up. So there's really this pattern of kind of increasing everything by 1 dimension every time as you go from the fully connected network to the 1D convolution to the 2D convolution, etc. We're now out of time for today, so next class we'll wrap up the course. We can do these true-false things from today that we didn't have time, and I'm going to see you in lab today and tomorrow.